Hi, my name is Qiangqiang Huang. I will be presenting NF-iSAM, Incremental Smoothing and Mapping via Normalizing Flows. This is a joint work with Dehann, Dehann, Fourie, Kasra, Khosoussi, Dehann, and John Leonard. The motivation of this work comes from three correlated issues in robot navigation. The first one is the inadequacy of point estimation for decision-making. For example, in collision-free navigation or active SLAM problems, we need to infer joint posterior distribution of robot poses and landmarks for uncertainty quantification. The second issue is the highly non-Gaussian posterior distribution in real-world SLAM problems. The non-Gaussian posterior can arise in nonlinear measurement and non-Gaussian noise models. For instance, the figure on the left-hand side shows a beacon localization problem via range measurements. The intersection of circles incurred by range measurements indicates multiple probable locations of beacon. The blue dots in the middle figure are robot positions after a noisy pose transformation. The banana-shaped distribution reflects non-Gaussian posterior. The right-hand side figure shows a Gaussian mixture for modeling sleep and grip states in robot motion model. Therefore, considering all those real-world problems, we need to handle non-Gaussian posteriors. The third issue is that non-Gaussian inference is in general intractable. So, we need efficient approximate inference techniques that can capture non-Gaussian uncertainty. There are many existing inference algorithms designed for SLAM problems. ISAM2 is known for using the Bayes tree for fast incremental update. However, it only provides Gaussian approximation of joint posterior. MH-ISAM2 is a recent extension of ISAM2. It uses Gaussian mixtures to model ambiguous data association or loop closure. Less likely modes will be pruned in subsequent computation. The algorithm is restricted to multi-hypothesis problem, and it cannot provide non-Gaussian joint posterior. Multimodal ISAM is another recent algorithm that exploits non-parametric belief propagation for inference and the Bayes tree for incremental update. However, it generates samples only from marginal posterior, not joint posterior. Fast SLAM is a well-known sampling-based algorithm. It suffers from the particle depletion issue, and it relies on Gaussian approximations for landmarks. In our work, we aim at an efficient non-Gaussian inference algorithm that can capture non-Gaussian joint posterior without performance degradation over time. And the algorithm will perform fast incremental updates when new variables are added and new observations are acquired. Here is our problem statement. We use a fact graph to represent a SLAM problem. The nodes with X or L denote latent variables such as robot pose or landmark location. The dark dots are factors. The unary factor F1 is a prior. The remainders are binary factors such as landmark measurement factor F2 and F4 and odometry measurement factors F3 and F5. Note that those factors can lead to non-Gaussian posteriors, as we mentioned earlier. The goal of this problem statement is to draw samples from the posterior distribution. Since the joint posterior is proportional to the product of factors, that product will be our target density for sampling. The first technical issue lies in the graphical structure. SLAM problems are usually high-dimensional and cyclic, so it's hard to sample the target density directly. The part 1 of our solution is to deal with this issue by the Bayes tree. From the perspective of the Bayes tree, the high-dimensional graph can be viewed as many lower-dimensional cliques. Each clique is a node on the Bayes tree, which also corresponds to a conditional probability if we refactorize the posterior distribution. With the tree structure, we can sample variables in the root clique first, and then, conditionally on those samples, we can sample variables in the child cliques. We keep doing that until reaching the leaves of the tree. In the specific example here, the two-node Bayes tree is equivalent to decompose the joint posterior by two conditional probabilities. From the root to the leaf of the tree, we sample x1, x2 from clique 2 first, and then sample x0 and y1 from click 1. A natural follow-up question is how to draw samples in a click. This is the technical issue 2 here. Now the target density becomes the product of factors within a clique. Since clique factors can be non-Gaussian or non-linear, it's still hard to draw samples from their product, even with lower dimensions. The part 2 of our solution exploits normalizing flows, which is a recent and powerful tool for modeling complex distributions. The basic idea is to learn transformation between normal distribution and the target density. And then we can transform normal distribution samples to the target space to get samples of target density. Here is an example of normalizing flows to show its expressive power. The transformation function t between random variable x and y is plotted in the middle. X follows a normal distribution and y is subject to a bimodal distribution. We can map samples of x to y by the transformation. The resulting samples of y are shown as the histogram on the right-hand side, which tightly fits the target distribution. We name our solution by normalizing flow, incremental smoothing, and mapping. In short, it's NF-iSAM. We emphasize the incremental update on this big picture. The top left figure is the old problem with old fact graph and Bayes tree. New measurements and variables will lead to new fact graph, which is on the bottom left. The right-hand side is the new Bayes tree. However, only part of the tree has been affected since the old one. The affected part is marked in green. We just need to learn normalizing flows on the affected nodes, and the learned model in gray node can be reused. This incremental step corresponds to the short blue arrow in the figure. After that, we draw samples from the root to the leaves of the entire tree to infer the joint posterior distribution. We summarize our contribution with a figure. Non-Gaussian, high-dimensional, and cyclic are three challenges we have about fact graphs, which are represented by rain clouds. Bayes tree and normalizing flows can help each other and construct a house of algorithms, which is NF-iSAM. With the capacity of efficient incremental inference and non-Gaussian probabilistic modeling, NF-iSAM can be robust to rain clouds of challenges. To be specific about contribution, we generalize ISAM2 to non-Gaussian settings, and we generalize normalizing flows to high-dimensional cyclic fact graphs. We will demonstrate NF-iSAM on two examples. The first one is a synthetic example. The scenario is that there are two unknown landmarks on the planar environment. In each time step, the robot will move forward, rotate in place, and take a range measurement with known data association. Here, the figure shows that at time step 0, the robot takes a new range measurement to the landmark L1. And then the robot proceeds to X1 and acquires a new odometry measurement and a new range measurement, which are colored in red. At time step 2, the robot moves to X2 and spots another landmark, L2. It moves on to X3 and gets a new range measurement and odometry measurement. Now it's at X4. At this point, there are already 3 range measurements to L2. The final post variable is X5. It returns to detect L1. So at the end of the day, each landmark is attached with 3 range measurements. Here we show samples drawn by different approaches. On the top left is NF-iSAM solution, in which the ground truth of L1 is marked by a plus marker, and its posterior samples are orange dots. It's not surprising that L1 is on a donut-shaped distribution, considering there is only one range measurement to it at this moment. ISAM2 solution is on the top right. It fails for this non-Gaussian posterior. The MM-iSAM on the bottom left is short for multimodal iSAM. The reference solution on the bottom right is found by a sampling package, which is considered more accurate than others. The NF-iSAM solution is the most similar one to the reference solution. time step 1, there are only 2 range measurements to L1, so its location is supposed to be bimodal. As you can see, iSAM cannot recover the non-Gaussian posterior. The NF-iSAM solution resembles the reference solution very well. And then the robot moves to X2 and starts detecting L2. Samples of L2 are colored in black, samples of X2 are in red. It's worth noting that the banana-shaped distribution of X2 will affect L2. Considering the donut shape incurred by a single range measurement, the distribution of L2 should be a mix of donut and banana shapes. Only NF-iSAM solution and the reference solution capture this fact. This is posterior distribution of time step 3. This is posterior distribution for time step 4. NF-iSAM solution and the reference solution are very much alike. At the final step, since there are sufficient measurements to landmarks, all the methods can pinpoint the landmark location by unimodal distributions. However, NF-iSAM captures the posterior uncertainty with the best accuracy. Our second example uses Plaza range-based navigation dataset. The sequence was acquired on a lawnmower robot equipped with ultra-wideband radar for range measurements. I'm going to show a video of NF-iSAM solution to the sequence. The landmarks are plotted with samples, and the robot trajectory is formed by average of pulse samples. The video demonstrates the smoothing capacity and the consistent performance over time of NF-iSAM. We provide a comparison with iSAM2. iSAM2 cannot solve the problem at the early stage due to non-Gaussian posteriors. The figures are the final estimations made by the two solvers. The scattered dots represent marginals. So, in the NF-iSAM solution, the very uncertain X400 pulse is on a banana-shaped distribution. This demonstrates the consistent performance of NF-iSAM on retaining strong non-Gaussian features in the posterior distribution. We end our results section with a quantitative analysis. The figure on the left shows statistical distance between our solutions and the reference solution on the synthetic example. NF-iSAM reaches the lowest distances across different time steps, which indicates consistently better accuracy than iSAM and MM-iSAM. The figure on the right shows runtime of different methods. Despite our Python implementation, NF-iSAM is faster than MM-iSAM. We conclude that we applied normalizing flows to spatial AI with non-Gaussian distributions. The proposed algorithm can generate samples from joint posterior distributions and has demonstrated advantages over alternative state-of-the-art SLAM techniques. A final key point is that we generalize iSAM2 to non-Gaussian settings.